Let's dive into a force that is quite literally all around us. It shapes our world in ways we can hear, feel, and sometimes in ways we can't ignore. We're talking about vibrations. So let me start by asking you a question. What's the hidden thread connecting the beautiful sound of a guitar and the terrifying collapse of a bridge? I mean, they seem worlds apart, right? Well, the answer might surprise you. And the answer is vibration. It's this incredibly powerful two-faced force. On one side, you have the controlled, beautiful shaking of a guitar string creating music. And on the other, you have the exact same principle, uncontrolled shaking that can bring a whole building down. It creates and it destroys. To really understand that power, we've got to start with the absolute basics. So let's pull back the curtain and decode the science behind every single wiggle, shake, and hum in the universe. Think about something super simple, like a pendulum swinging. That steady, back and forth swing, that's the heart of it all. It's called oscillation, a repeating motion around a center point. This is where the whole story of vibration really begins. So here's the official definition for you. Vibration is just the to and fro motion of an object around its resting or mean position. That's it. From that pendulum we just saw to the invisible jiggling of atoms in your desk, it's all the same fundamental idea. Okay, so if vibration is the motion itself, then frequency tells us how fast that motion is happening. It's just the count of how many of those back and forth cycles happen every second. A slow swinging pendulum has a low frequency, but a humming guitar string, that has a super high one. And if frequency is the speed, then amplitude is the size of the vibration. It's all about how far the object moves away from that resting point. A really gentle swing has a tiny amplitude, while a violent, rattling shake has a huge one. You know, when we map this motion out on a graph, it creates this beautiful wave shape. And the highest point of that wave, what we see here labeled as A, that's the amplitude. So a bigger A means a more intense vibration. Simple as that. Now, let's build on that. Because it turns out, whether you're talking about a massive skyscraper or just your washing machine on spin cycle, every single vibrating system is made of the same three core parts. Let's take a look at the anatomy of a shake. This might look like a simple little diagram, but honestly, this is the blueprint for pretty much every vibrating system engineers deal with. You've got your three key players: a mass, a spring, and something called a damper. And each of these parts has a really important job. The mass is the thing that's actually moving, and it stores the energy of that motion. The spring gives it stiffness, and it's always trying to pull the mass back to the middle. And then you have the damper. Think of it like a brake. Its job is to slow everything down. Now, understanding those three components is absolutely crucial because it's the key to unlocking the most powerful and sometimes the most dangerous phenomenon in the science of vibrations, something called the resonance effect. See, every single object from a huge bridge to a delicate wine glass has what we call a natural frequency. You can think of it as its own personal favorite rhythm to vibrate at. It's just like pushing a kid on a swing. You know how there's a perfect timing to your pushes to make them go higher and higher? That perfect timing is the swing's natural frequency. So, what happens when some outside force, maybe it's the wind or an engine's hum or even a sound wave, starts pushing on an object at its exact natural frequency? What you get is resonance. It's amazing. When you strike one tuning fork, its vibrations travel through the air. And if those sound waves hit another, identical tuning fork, they match its natural frequency perfectly. That transfers the energy, and it causes that second fork to start vibrating like crazy, all on its own. So, to put it simply, resonance is what happens when an external push perfectly matches an object's natural rhythm. When that happens, the amplitude, the size of the vibration, can grow to be excessively, sometimes dangerously large. This is the secret behind an opera singer shattering a glass, and it's the exact same phenomenon engineers fight to prevent in bridges and airplanes. And that brings us to our final section. Now that we get just how powerful these vibrations can be, let's talk about why controlling them, taming the tremor, is so incredibly important in our world. In the real world, unwanted vibrations are a huge problem. I mean, they can be caused by anything from an unbalanced motor to just old, worn-out parts. And the effects, they're serious. We're talking about unwanted noise, parts wearing down way too fast, catastrophic failures, and just plain bad product quality. Just take a look at all this industrial equipment. Pumps, motors, fans, you name it. For every single one of these, engineers have to design them specifically to keep vibration under control. This isn't just about making things run smoothly. It's absolutely fundamental for safety,
for reliability, and for performance.
So, from the gentle hum of your refrigerator to the bounce you feel in your car's suspension, vibrations are just this integral hidden part of our world. The real question is, now that you know the science behind the shake, where are you going to spot them next?